So I made this really cool Gauss's law program that visualized Gauss's law with the cube. And I don't want to talk about how to make that program. I want to actually show you why I made that. And so to start off, let's talk about Flux and Gauss's law. So I made this. Here's just a quick picture. This is rain flux. So imagine that you had like a sheet of paper like this, and rains. It's raining, and you want to measure how much rain hits that paper. And so it depends on three things. It depends on one, how fast it's raining, how much rain is coming down, and then depends on the size of the area and the angle between the area and the rain. And that's rain flux. And we can do the same thing for electric field. So the electric field flux, I'm going to show you a demonstration of this. And the point is, I didn't even put it right here. So this is the flux is electric field area, and I left off the most important thing, Gauss's law, which says that the electric flux is proportional to the charge inside of a closed surface. And so you can use Gauss's law to determine the magnitude of electric field for some situations, but I think some people kind of get out of control for it. So let's just start with some programs. And so I put these programs in this is a glow script and not what I normally use, which is Trinket. And so this is my actually animation of the electric field due to a point charge and a Gaussian surface. So if I pick a sphere, then I can calculate the flux of the whole sphere because of something very important, and that is that the electric field is always perpendicular to the area. And if I have the sphere centered on my charge, then the magnitude is the same in all these different spots. And so I could just calculate the electric flux is just the value of the electric field times the surface area of the sphere, and that would make it easy. But in order to use that, you could calculate the magnitude of the electric field or the expression of the electric field as a function of distance. And that's usually what you do in class. But what if it's not a nice surface like this? That's what I want to look at. Okay, so what happens if you don't? And let me see if I got these in the right order. Okay, yeah. So here is a program that I calculate the flux. So I know we can move this around, but here's my charge, a positive charge, and here's some area. Now, if I have just this rectangular area like this, calculating the flux is kind of difficult, right? Because you'll notice I have plotted the electric field at different points on this surface, but it's not constant. The electric field over here is different than the electric field right there, both in magnitude and direction. So you can't just say electric field times area in this case. It's not so easy. Now, what I did was I took my whole area, this whole big thing, and I broke it into 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 4 by 9 squares. And then for each one of these squares, now the electric field on this square is fairly constant because it doesn't change too much in distance from the point. And so I can just say, okay, it's that electric field times the area of that squared plus that electric field times the area of that square, and so forth. And so you can calculate the flux through that point charge. We can edit this. We can even move that point charge. Let's say it's at in the z direction. Let's just try this 0.5. What if I put it right there? So now you see it's up there. That looks pretty cool. And there's my electric field, and I calculate the flux and everything like that. Okay, that's not Gauss's law. Gauss's law says, what if I have a complete surface? So here is, let's see if I think I got this in the right order. Run this program. Yeah. Okay, so this is a charge moving into a Gaussian box. It's not a real box. I'm going to run it multiple times. Okay. And in this case, one of the things I did is if the flux is positive, then, so a positive flux, if I have the electric field due to this charge going into the box, pointing inside, let's edit this. Let's run this until for a shorter amount of time. Let's see, edit the code. Wow, let's put it while 0. Okay. So now while this is negative flux, okay, but because the electric field is pointing away from that positive charge into the area, Now, right here, it's going to be in the inside of the sphere, the box. And you'll notice that the electric field's always pointing outward of the box. So you have positive flux, and that's red cubes everywhere. I also made the opacity of the square proportional to the value of the flux. So the parts up here where it's brighter, there's higher flux, lower flux over there because the electric field is smaller. Okay, so let's just put this, while x is less than, what did I put that? Let's say -1. So at this point, the box, the charge is outside of the box. Now, this is Gauss's law. You'll notice that this surface has a negative electric flux because it's blue. And also because, if you think about it, the electric field is pointing into the surface. So it's in the surface, the area is pointing out from the volume. So that's a negative flux. But the total flux in the whole cube is 0 because once that electric field goes through into this wall, now it's going out of all these other walls and they're all red. So they're not as bright, but there's more of them. So the total flux is 0. And let's see if you can, it's close to you can kind of see that right here. I'll show you a better graph in just a second. Inside, the total flux is not 0. The total flux is positive. That's because I have a positive charge in there. And then once it gets, again, outside, it's negative. Okay. So let's run this again. I said this was originally while x was less than 1. I think. Yeah. And let's run it in this little bit slower speed. 50. Okay, so here it is. It's coming into the box. This charge is moving. We're going to look at the total flux too. So once it gets into the box, what happens? Once it goes into the box, the total flux jumps up to some constant value. It doesn't matter where in the box it is, as long as it's in the box. Now, you couldn't easily calculate this as a numerical, as a normal integral because it's really a complicated situation. But watch what happens as soon as the charge leaves the box. The flux is going to go back down to 0. And there you go. No charge in the total flux. This is the total flux in the whole cube, not on one side, the total flux. And you would never see this as in Gauss's law because it's not very useful. Okay. Now, what if I have a dipole? So here's a dipole, and here's the electric field due to a dipole. So if you take a location, say right here, this is a positive charge, and that's a negative charge. So this point right here is closer to the positive charge. So it's going to have an electric field pointing away. There's a negative charge right here, but it's further away. So there's the electric field due to the negative charge is pointing to the left. But if you add those two together, you get them pointing to the right. Now, if I'm up here, the electric field due to the positive charge is up at an angle that way. The electric field due to the negative charge is down this way, and they add together being completely horizontal. So you get this cool pattern like this. Now, but what happens as this charge moves into a Gaussian box that I made? Let's find out. You see, I have all these programs put together. Why did that run? Okay, let's see this run it again. Okay, so here you see, let's run it first in full time. That positive charge creates a negative flux. This one, once it gets inside, now the total flux is 0. I'm going to show you that in just a second. Watch what happens when it leaves. So again, this negative charge, the electric field is pointing into the box. So, I'm sorry, away from the box because that's a negative charge. That makes that a positive flux. But you'll notice the flux over the whole box is close to 0. It's red on that side and 0 on the other side. So let's do this watching the graph. Run it again and let's watch the graph. So once that first one goes into the box, it has a positive flux. The negative one gets in the box. Now the total charge inside is 0 and the flux backs down to 0. Now when the positive charge leaves, now there's a negative charge in there, and that makes the total flux drop down to 0. Once they're outside, it goes back down to nothing. 0. Okay. So that just shows you how we can make this relationship between the total charge inside the box and the total flux. And again, this is not a useful situation. This is a non-useful situation because you couldn't easily calculate this to use it. I did the other way. I calculated electric field to calculate the flux. Okay, let's see. Let's go back over. I'm trying to think of other. Yeah, I think that's good. We can move this around. You can put this. I had this off center. Actually, this one off center. We can change that. I can put it right in the center if I want to. You can make it move in all sorts of different ways, but it's just fun to watch. And I'll give you this code so you can play with it. I really like this. Now there are some things you got to change, like how do you get this opacity to work out right? You have to pick a value for the maximum flux so that it can kind of scale the opacity in different ways. But I think I'll just stop there. I'll include a link to a couple of the videos down below in the code so you can play with it and have fun. But there you go. Flux. Gauss's law.